Welcome back to our C++ parallel C++ class for scientific computing. I'm always glad to see that people come back. That tells me that at least there has to be some interest in these things. By the way, I'm always open to feedback. So if you feel that things have been too terse or I glanced over certain details you're interested in, please let me know. The other thing, I opened the second assignment, so you should have seen that on the web page, so you can start working on that. Again, the instructions ask you, at least for the first part of the assignment, to discuss things on Discord with your colleagues, with your other students in the class, because there are some things I really would like you to discuss and to come up with answers collectively. Okay, so don't be shy and discuss these things on Discord. Okay, what I want to do today is I want to talk about fixed point computing, fixed point calculations, and finding roots. Anybody knows what a fixed point is of a function? Have you ever tried to use your calculator, enter an arbitrary number and hit cosine? And you keep hitting cosine over and over and over again. And you will see that the number kind of asymptotically gets closer to a constant that doesn't change anymore. This is a fixed point of the cosine function. Finding roots are algorithms that allow us to find the intersection point between a function and the x-axis. So where the value of the function is equal to 0. Okay, so formally C is a fixed point of a function f. In the following preconditions have to be met. C has to belong to both the domain and the codomain of the function. The domain is a set of values that are allowed for the arguments, and the codomain of a function is a set of values the function can return. So C has to be part of both sets of that function, and if you call f with the argument of C, you get as a result C back. So it's the same constant thing you get over and over again. Algorithmically, we calculate that by we generate a sequence of numbers by calling f repeatedly on the previous value we got back from the previous invocation for arbitrary number of iterations. And if that converges to a value x fix such that the function returns the same value as its argument, then f x fix is a so-called fixed point. There are some examples. For instance, cosine, I already said that. Cosine is probably the most well-known one. Another polynomial, just for the sake of it. There are many contiguous functions that intersect the y equals x function that have a fixed point there. It's used in a very widely. It's used in economics to study the existence and stability of some equilibria. It's used in physics for phase transition modeling, in computer science for designing algorithms and for optimizations, in engineering for control systems, stability of structures, numerical root finding, and so on and so on. So there's a very broad range of applications of fixed point calculations. I'm using it here in this class because it gives me a good opportunity to introduce the concept of generic functions. And we will see how that works and what that means. So it's, again, a vehicle to talk about C++, language features of C++, and how you can use C++ for your needs in an efficient way. Let's start with cosine. So if you... yeah, I started the lecture already. Thank you. If you look at it and write a simple function that calculates a fixed point of the cosine, it takes two arguments, the number of iterations I want to compute it over, how often do I want to call cosine, some initial value in it, And it's a simple for loop that goes from I0 to the number of iterations and calls cosine repeatedly and returns the overall result. Very simple. So if I call that function with an increasing number of iterations, right? So in this case, from 1 to 85, I'm calling my fixed point function, passing the number of requested iterations and some initial value there, and print the result. What I get is something like this, right? So you can see that the value gets closer and closer to the fixed point, and in the end, after around 85 iterations, at least for the floating point resolution, the value doesn't change anymore. If you look at, if you want to understand how to geometrically interpret that, it's very simple. We have the cosine, which is the red line. The green line is the y equals x function. And the fixed point is essentially just getting closer and closer to that intersection point of the two functions by iterating over the value and applying the value again and again to the input. So it's a very simple geometrical interpretation. We wrote that function for cosine, but you probably want to use it for something more general purpose, not limit yourself to applying to cosine, but you want to be able to pass an arbitrary function that takes one argument and returns a result. And you want to apply your algorithm, because what we're doing is developing an algorithm to that function. And as you can see, the simplest way in C++ is just to pass a function as an argument to another function. In this case, our fixed point algorithm now expects a function that takes one argument, which is a double, and returns a double. And the other two arguments, the max iterations and the init, hasn't changed. Our argument is f, so I can use f as a function now in my loop, and I can apply this algorithm to an arbitrary function f. So when we call that in our main routine, then we suddenly have a problem. What should we pass to the fixed point as a first argument? You have seen it in Python. You can pass functions to another function. You have seen it in Java. You can pass functions to other functions. So it's a facility that is essentially provided by all programming languages. But I would like to talk about how to do that in C++ in the easiest way. So what should go here in the first argument? Just in the simplest case, if you want to calculate the cosine again. So as I said, it looks a bit strange, that syntax. You say double f, parenthesis double. And this is just a notion of telling the compiler, hey, I'm passing a function with this prototype. You can pass any function that takes one argument double and returns a double itself, and pass that to that function. So if we create a named function, let's call it calculate cosine, which conforms to that expected prototype. It takes one argument and returns a double and does nothing more than calling cosine in our case. Then we suddenly can pass that calculate cosine function as a first argument to fixed point, and that's it. So this code is completely equivalent to the code I wrote before. It will compute the fixed point for the cosine function in the same way as I showed on the first slides. Okay, anybody knows that person? It's a very famous person. One of the luminaries of the computer science history. Well, it's Alonzo Church. You might have heard of Church logic. He has developed a whole set of various theories and formalisms that can be applied to come to a broad range of computer science problems. And the reason why I'm mentioning him here is because he is the author of the Lambda calculus. Probably everybody has heard about Lambda calculus. It's a formalism that describes how you can operate with functions and turn functions into higher level functions by passing to other functions and reason about these constructs. The reason I'm introducing him is because I would like to go back to what I actually already used in the last lecture, to lambda functions in C++. Because lambda functions are essentially anonymous functions, are functions that don't have a name. And I want to introduce that in the context of our fixed point algorithm in more detail, because it's a very useful facility that we will use over and over again. And we will stop kind of highlighting it very, very soon. So instead of using a named function, which was a calculate cosine function I defined, I use a lambda function, and I will explain what that is and where that comes from in a minute, which takes one argument, which is a double, which returns a double, and has a body which calculates the cosine. The benefit of using lambda functions is that you don't separate the definition of the function from the use of the function, right? Sometimes it's very inconvenient if you have to define a function in one place and then you have to use it in another place, and all you need is to use it once. It's very difficult for people to follow, to understand the code. So it's much easier if you can just drop in the function where you actually use it, and everything is defined in one place. So let's talk about what does that syntax actually mean. We started off with our calculate cosine function, and the first transformation I want to do is, instead of telling the compiler that the function returns a double, I use a different definition syntax that is valid in C++ that actually tells the compiler, hey, please figure it out for yourself. What is that return type? Uses auto, and then specifies the return type after the the prototype of the function with that arrow semantics. These two things are completely identical, so you can use the second way of declaring a function everywhere if you want, but you have to use a second way of declaring a function when you're dealing with lambdas, because lambdas can't be used or can't be defined in the first way. So let's go ahead. We have that now, that alternative syntax of defining a function, but if you rewrite that slightly differently by say, okay, now I define a variable, calculate cosine, which equals to a function that has no name. And that function here is a lambda, which takes one argument, returns a double, and does the same thing as before. So you see, a lambda is very much the same as a normal function in C++. It's just a function that doesn't have a name. So whenever you see the brackets in front of an argument list, you know, okay, this is a function like any other, just the programmer was too lazy to give it a name. That's all. Please note that lambdas are distinct from each other. Even if you define the same lambda twice in the code, these two functions have different internal names and are separate. They are not the same things. Okay, so a lambda function is a function that has no name. Otherwise, it's the same as a named function. It has arguments, it has a return type, it has a body. The return type, though, is optional if the compiler can figure it out for itself. So in this case, it's clear that there's only one return statement, and that return statement generates a double. So return type has to be a double. So why write that if the compiler can figure it out for us? The other thing is that, and we will see that there's an additional what's called a capture clause, things that might go in between the two brackets, and we will use that later on, and I will explain it as we go. So to go back to our example, to our fixed point algorithm, we can now write it in this very terse way. Please note I left off the return type because the compiler can deduce it from that one return statement. Otherwise, it's completely the same as before. So it's a very terse, very nice way of passing a function to an algorithm. And we will do that very often because starting next lecture, I will start talking about algorithms in the standard library and data structure in the standard library. And you will see that all algorithms in the standard library are actually expecting you to provide a function to it. Because what we have done is we have created an algorithm which generically captures the essence of the algorithm, but the user of that algorithm customizes the implementation of it by providing a function, gives it a very specific meaning, right? In this case, finding the fixed point of a cosine. So we separate the essence of the algorithms from the concrete implementation, from the concrete use of that very same algorithm. Okay, so far so good. I think it's not difficult to understand. It's a very simple loop in the end that iterates over a repeated function invocation. Okay, so let's try to find a root of a function with the fixed point algorithm we just developed. What is a root of a function? So if we say we have a function y equals f of x, then in order to find its root, which means find the value x for which f of x is equal to 0, we want to find want to use a fixed point iteration as follows. First thing we need to do, we convert our f of x to a different representation which says x equals g of x, where g is a different function from f, obviously, because we have kind of pulled out one of the x's to the other side. Now, when we start with an initial guess of x0, which is close to the actual solution, and we iterate over computing g of x repeatedly for n from 0 to some upper limit, if that sequence of numbers we get converges to a limit, let's call that limit r, and the function g is contiguous at that point, then the limit r is the root of the original function we started off with. So if we can use this transformation in order to find the value r, which makes f of x equals to 0. Okay, so let's try doing that. Obviously, the real trick in this is to find the proper transformation such that g of x has a fixed point. Otherwise, it will not work. And not all transformations that turn f of x into some equivalent representation have a fixed point. So you might be lucky when you do that transformation, it might not work. And we will see some examples in a minute. So let's look at an example which says x to the power of 3 is equals sinus x, sine x. I just gave you the both functions, that's x to the power of 3 and sine of x. You can have different transformations into that x equals to something representation. It could be sine x over x squared, it could be the cubic root of sine x, and so on and so on. And there are many ways you can do that. And as we will see, only some of those actually have a fixed point, and some don't have a fixed point. They don't converge. Here's a table which does that for 4 different transformations. Cubic root of sine x over x squared, and so on, over a large number of iterations. And as you can see, actually only these two converge. The others diverge. They don't give you the result. You might wonder, what is that mu? Well, mu is just an error measure that gives us the ratio of the difference from the current time step over the previous iteration. So if we get not a number, that means that this turned into 0, which means that we actually hit the point, right? So that allows you to determine whether you actually reach the convergence point or not. Okay, so let's change our fixed point algorithm to support that, because what we now need is an additional termination condition. We need to be able to say, okay, I reached my result. There's no point in iterating further. The way we do that is we introduce another argument, let's call it epsilon. And that epsilon gives us the difference at which point we want to stop the iteration, right? When the difference between the previous iteration and the current iteration is smaller than epsilon, then we have obviously reached a convergence point. And we have to add an additional condition in the middle, which says, okay, if the current value minus the previous value, the absolute value of that difference is smaller than epsilon, well, then we are done. No reason to continue. Please note that I'm using a default argument for epsilon here, which in C++ means if the function or the algorithm fixed point is called with 3 arguments only, then 10 to the power of minus 10 is used as a value for the epsilon. But you can specify 1, and then the specified 1 will be used. Something many languages have. Just wanted to introduce it in this context to give you an idea how you can do that with C++. Okay, let's continue. How can we turn this? Well, if you look at, okay, give me a second. If we use this in our main function, now we have a lambda, which is using a float type, which I have defined before. In this case, the float type is double. And otherwise, it's doing the same as we were doing with the cosine, but this time it just calculates the cubic root of the sine of x. Otherwise, the other arguments are the same. The other thing I want to introduce here, and by the way, we haven't talked about using streaming operators for output in C++. I always have used the print statement, the print function before, but we will see that interchangeably over time in different variations. What that essentially means is Cout represents the console output, and the left shift operator here, that smaller, is used to encode outputting what comes after to the console. And you can chain these operations. As you can see, I'm outputting the integer, then I'm outputting a string, then I'm outputting the fixed point result, and so on and so on. Another thing I want to add here is a way to control the number of digits that are being printed to Cout. Because Cout normally restricts the number of digits to, I don't know, 5 or 6 digits after the decimal point. But we really want to get the maximum precision here when we print it to the screen. So I'm asking a library facility, which is called numeric limits. Please tell me what is the number of digits you can represent for a double type in this case. And I set the precision of that streaming operation to that size. And we will see in a minute why we need that. Here's the output, what we get from it. As you see, it starts converging at around the 16th, 17th iteration of our computation of the cubic root of sine. Right, just to highlight that. It essentially converged at these 2 iterations. What if we want to have a higher precision? Doubles are floating point numbers that are built in, that are supported by the hardware, but we know that they can represent only a certain number of digits overall, because it's 64 bits, so we have only a limited set of availability in terms of what amount of real numbers can we represent. So what I want to do is to use the same code I had before, with the only difference that instead of using the double float type, I'm using a library type which is defined in Boost, and you can Google that. It's, by the way, a very nice library of a vast variety of C++ facilities. In this case, I'm using a float type that actually can represent 100 digits. Not just 13 like that double type, but I can represent floating point numbers with a precision, with a resolution of 100 digits. Okay, I'm getting this. And as you see, it actually converges at 16 or 17 iterations, because from that point on, even the 100 digits don't change anymore. So we can assume that we really reached the fixed point of the function. We found the root of our initial function. One thing I have to mention, look, here I'm using the same fixed point function with a completely different data type. It's not double anymore. It's a CPP bin float 100 type, which is defined completely independently of the C++ standard library. How does that work? Well, if we were using our fixed point algorithm the way I defined it, it wouldn't work. If you go back, you see that it expects a function that takes a double and returns a double. But we give it a function that expects a 100-digit floating point type and returns a 100-digit floating point type. So what can we do that we still can use the fixed point function or fixed point algorithm for different data types? Well, this is the original algorithm we developed so far. So what I'm doing now is I turn that into a template. We talked about templates in the context of template types, where I said a template type is a type function, which takes one set of types and gives you a different type back. A template function is a different beast. It has nothing to do with type conversions. It's a way to make a function generic. It makes a function generic in the sense that you can call that function with arbitrary arguments, with arbitrary argument types. And the compiler will figure out which types you actually used. So in this case, I define one template argument, which I called float. And now my function actually doesn't take a double and returns a double, but takes a float and returns a float, where float is not specified in that context. It's a template argument. It's a parameter that the compiler will use to generate the correct function. And obviously, the initial value and the epsilon value should be of the same data type. That's why it's float as well. And the overall fixed point will return that very same type, because otherwise it wouldn't make sense. Okay, now let's write the same function again. We initialize our initial value. We have the set of iterations. We compute, call f with our current iteration variable. We check for the epsilon, and if we are close enough, we break our loop. So in the end, it's absolutely the same code as before. The only difference is that instead of using double for all these arguments, we use the name of the template argument we specified. And that makes both codes I showed before compile out of the box. The one that is using double and the one that is using that boost float 100-digit type. And as we will see, it will work for any other type as well, as long as those types have certain properties. And we will see a couple of examples of that. Two more fixes or two more changes I want to apply to that fixed point function. Well, the first one is the caller might be interested in knowing whether it actually the function ran out of iterations, which usually tells you that there was no convergence, or whether the function has converged. This way it's not possible to tell, because in both cases it returns the current value of x, and you don't know, is that my result I'm looking for or not. So what I want to do, I want to return two things from that function, namely the value itself and the number of iterations taken up to that point when that value was generated. So I'm returning a pair. Standard pair is a utility type you can use. It's defined in the standard library. In the very first or second lecture, we talked about singleton, right? It's a regular type that embeds one other value. A pair is the same thing, except that it embeds two things. And you can specify which types you actually want to store in that pair. And in this case, I want to store the result type, which is, well, I have renamed the template argument to data. for reasons we will see why I did that in a minute. And I want to return the number of iterations reached at that point to the user so that the user can see, okay, I passed in 100 iterations, I got back 100 iterations. So I know that I ran out of iterations, so I didn't get my result. The second thing I want to do, instead of explicitly checking for the difference between the previous and the current iteration and comparing it with the epsilon, I want to generalize this expression as well. I want to leave that to the user to define the termination condition of my loop. So that's why I added another argument, which I called cont, which, as you see, is another function which expects two of those things and returns a bool. The two of those things are the previous value and the current value in our iteration. And it can figure out whether these two values actually tell us that we reached the convergence point or not, and will return true if it reached the conversion point, and if it didn't, then it returns false. Otherwise, it's very much the same. So if you rewrite that function this way now, what we will see is that instead of using double, we use data here as the loop variable. We calculate our function, and then we call our condition with the previous and the current value to see whether our termination condition is met or not. And if it is met, we will return the current value and the current number of iterations. And if we run out of iterations, we return the last computed value and the overall number of iterations that was passed in. So it gives the user the means of deciding whether the iteration was successful or not. Okay. Otherwise, nothing has changed. So again, what we have done, we have developed an algorithm, and that's the final version of that algorithm. I will not modify that further, which encapsulates the general logic of doing fixed point calculations. But it leaves open the actual computation of the value, and it leaves open the termination condition. And those two things have to be provided by the user when that algorithm is being used. So we nicely separated the general logic from the concrete implementation for a particular case. So how would that look like now for our example? Well, the first argument is still the same. We want to compute the cubic root of the sine of x. But now we pass a second lambda function, which expects two arguments, the previous one and the current one. And all it has to do the same what we have done before. It compares the two values and looks if the difference is smaller than some margin. Absolutely the same effect as before. But now we have a general purpose, generic algorithm which will work in many situations. And you customize that algorithm by supplying your own functionality to it. Okay? Any questions so far? Good. I just wanted to add an exercise if you really want to play with it. What about if you just use an arbitrary function? Play around with it. This is an example where I know that it will converge. Convert the given function into that g of x equals x form. Answer the question, how many iterations do you need to reach a certain precision? Estimate the solution. And if you want, just create a plot that has the three functions on it. F of x, g of x, and y equals x, that straight line. And perhaps show how things are closing in to the convergence point, like I showed in the very first slide with the cosine, right? Where you have seen that narrowing down to the intersection point. Try it out. It's not difficult to do, but might be a nice example for you to play with. And by the way, feel free to use a fixed point algorithm as defined on the slides for that. So you don't even have to write a loop. You just call that fixed point function and have to supply 2 or 3 additional arguments to it. Okay. Finding roots using fixed point. Fairly straightforward. Okay, so now let's go to the next topic, which is how do I find the square root of a number? How would you calculate the square root of a number if I ask you to do so? Well, without calculator. Any idea? Anybody?
Long division method. Division method, long division.
Okay, I don't know what you mean, but you're probably right. Well, you have to divide it somehow, right? You have to somehow narrow it down. There's an algorithm developed by an ancient Egyptian mathematician 2,000 years ago, which works as follows, which says that the square root of a number a can be iteratively computed by averaging the current approximation and a over the current approximation. Which makes sense, because if xn turns into square root of a, then this equation suddenly turns true, right? If I put square root of a here, it's square root of a plus a over square root of a half gives you square root of a. You can just do the math yourself. So it's a well-known, very old algorithm, and I want to implement that here just to show how we can use our fixed point function to do that. Because as you again see, what we have is a repeated invocation of the same function with the previous result over and over again. So it's again a case to use our newly developed fixed point algorithm. If we implement it without the fixed point algorithm, it would look like this, right? We start with an initial value, we have a loop that does a certain number of iterations, and we compute the next value of our iteration by averaging x and a over x, where a is the value we want to find the square root for. The average function obviously is just the sum of the two values divided by 2, right? The middle point between the two values. But as I said, it's essentially the same what we've been doing for our fixed point algorithm. So why not use the fixed point algorithm instead? Well, this is what we get. I just pass in a lambda, which calls my average, pass in n, the number of iterations, and an initial value. The only thing that is new is that I put the a in the square bracket here, which is called the capture clause of the lambda. And in Python, when you define a lambda function in Python or a local function in Python, it automatically has access to all variables of the surrounding context. In C++, that's not the case. So a lambda function, by default, doesn't have access to a, which is defined outside of the lambda function. So in C++, you have to explicitly list all the variables you want to make available inside the lambda function in the capture clause. Okay? But otherwise, this is your square root algorithm. It will work. It will just do what you expect. Any questions about that? And by the way, as you can see, I made that iterate square root function a template function itself, so I can use it with different data types if I want to. So I can compute square root to an arbitrary precision in the end by supplying different data types to when calling the iterate square root function. That's the square root. Easy as that. Okay, let's have a look at other algorithms that allow us to find roots of a given function. Roots in the sense of at which point x is the value of the function equal to 0. And there are several algorithms available. I want to talk about three algorithms today. It's a so-called bisection algorithm or bisection method, the Newton-Raphson method, and a very widely used algorithm in machine learning, which is called gradient descent. And we will look at these algorithms, what they do, and we will implement them. So let's assume we have a nonlinear function f of x, and we want to compute the root, which means it's the value of x where that function, the value of the function is 0. So in this case, it's essentially in 3 points, right? This function has 3 roots. To find a root of a continuous differentiable function, and assuming the root is near of x equals x0, we can apply some iterative algorithms, and I will introduce those in a minute. So let's start with the bisection method. It's not difficult math, so I will not dwell on the math itself. You will understand that, and if not, please ask questions. Essentially, the idea is there is a intermediate value theorem which says that if I have a function which is defined between a1 and b1, and the sign of the function in a is different from the sign of the function in b, and the function is contiguous, that means that there has to be some point in between a and b where the function is 0. Otherwise, the signs wouldn't be different, right? So what you can do, you can bisect the interval. You can say, okay, I see that these two have different signs, so let's find the middle one and continue the process between the middle point and a, and bisect it over and over again until you get close enough to the actual solution. So let's assume the root of a contiguous function is inside that given interval, x1, x2. Then we divide that interval into two sections, from x1 to x0 and x0 to x2, somewhere here in the middle in the simplest case. If the signs are not equal, then I repeat the recursion for the first interval. Otherwise, I repeat the recursion for the second interval until my value of the function is smaller than epsilon, because at that point I know that f actually is close enough to 0, so I found my solution. Easy as that. Okay, let's try implementing that. Okay, I define a function which I called bisection, which takes our function double, which expects a double, which returns a double, number of iterations. Now I need two values, right? The minimum and the maximum interval I want to bisect over. xn and xm and an epsilon. What the function would do, it computes the values of the function at the 2 points of the current boundaries of my current interval. If one of those functions is smaller than epsilon, then I return the current iteration and the current value. Otherwise, I find the next boundary by finding the midpoint between the current boundary points. And if the signs of these two are the same, I go to the left one. And if the signs of the two are different, then I just change the upper bound to the new middle element and rinse repeat. Very simple algorithm. Now you might say, from a distance, doesn't that look like fixed point? It's a fixed point computing. The only difference is that here we don't compute, we don't have one value we compute over and over again in our loop, but we have two values, namely the boundary values, right? The loop is being called with two values which give us the current boundary, and the result of that loop should be the new boundary, either with a changed upper or with a changed lower bound of our range. So let's apply our fixed point algorithm for exactly that. Okay? So, as I said, we now have two values we have to deal with. So we can't call our fixed point by supplying just a double. We have to give it two doubles so that it can return us the new boundary after the iteration. So I define a new type, which is again a pair of two doubles, assuming that the first double is the lower bound and the second double is the upper bound of my current segment. And then I call the fixed point function, and as initial value I pass in a stud pair of my initial bounds of what the user wants to iterate over, and I have to supply two lambdas. And please note, those lambdas now expect that pair as its input and return that pair as an output as well. So what we do, we compute the function value on the first element of our pair. It's called dot first. Then we compute the midpoint between the two, which is just the sum of the two divided by 2. And then we do the previous logic. If the sign of the left boundary is the same as the sign of the middle point, then we do one thing, otherwise we do the other thing. And we return the new boundary, the updated boundary, from our lambda so that the next iteration can recurs into the appropriate section of our interval. And the termination condition is simple as well, because in this case we don't even need the previous value. We just ignore it, and we look at whether the function values at the left or the right boundary actually have become smaller than epsilon, and if yes, then we are done, otherwise we have to continue. So as you can see, again, we are using our fixed point algorithm as defined on slide. And this time we tell the compiler to actually use a completely different, well, kind of type. It's not a floating point value anymore. It's a pair of two values. And the compiler will still use our algorithm as before, and we will be able to customize that fixed point algorithm we defined with our two lambda functions, and we will get exactly what we want. I think that's the whole essence of these generic algorithms, the whole standard library is built around, and a lot of C++ code is built around nowadays. That you try to separate the essence of the algorithm, in this case, the iteration and invoking the termination condition, from the concrete use case where the algorithm has been used or has to be used. And as you can see, we don't have to worry about loop boundaries. We don't have to worry about how all of that is implemented internally. All we say, okay, use my fixed point algorithm, which is defined somewhere else, use this as a reinitialization condition, and use this as a termination condition for my fixed point, and that's it. And I can use arbitrary types to customize it. It doesn't have to be a double or a 100-digit floating point value, floating point type. It can be essentially, in this case, a pair of doubles or anything else. Any questions so far? Okay. So what I'm trying to do here is to convey that making functions generic is very beneficial, because they suddenly are usable in contexts the original writer of the algorithm didn't even imagine that they can be used in. Right? When we developed the fixed point algorithm, we didn't think of that we can use it for a bisection algorithm or for something else. Okay, let's talk about Newton-Raphson method. You have heard about that. Newton-Raphson method is another method that allows us to find the root of a function. And the way that method works is that you start off with some approximation of the result, which is xn. You look at the slope of the tangent that is describing the function in the point of x, and get a new value on the x-axis by just extending that tangent, which is closer to the root than before. And it converges very fast. You get very quickly closer to the root. Actually, it converges quadratically. So it's a very, very fast conversion. If we do that in a formula, well, this is what the iteration formula is. The next x value is, you can compute that by using the current x value and divide the derivative of the function in the point of x over the function value, and you get the next iteration. Everybody knows what derivative of a function is? You should remember that from your calculus classes, I believe, or function analysis or whatever. Essentially, the derivative is the slope of that tangent. It's the tangent of that angle. That is the value of the derivative of the function in this point. Just a bit more general, for a univariate function, so a function that takes one argument, the gradient at x is simply the value of the first derivative of that function at point x. As I said, it's just the tangent in the point where I want to calculate the derivative. Just an example. Let's say we have that polynomial. The derivative is that other polynomial. And if we set f of the derivative to 0, then we even can compute the extrema. Because, well, for our function f, in the extrema points, the derivative is equal to 0. So we can apply all of that also to compute the extrema, essentially. We can solve optimization problems by using the Newton-Raphson method. And I will talk about that in a minute, a bit more detail. OK, so let's implement it. A Newton function, now it takes two functions, actually. It takes the function f we want to analyze, we want to find the root for, and it takes another function, which I called f prime, which is a representation of the derivative of the function f. And from that point on, everything is simple, because we compute f. If f is smaller than epsilon, we have found our result. Otherwise, we compute the derivative at that point and get to the next iteration value by just applying the formula I just derived, by dividing the derivative over the function value and subtract it from the current iteration value, and continue. Again, doesn't that look like a fixed point? Yes, it is fixed point. So let's turn that into a fixed point. But before that, what I want to do is, what I don't like here is that I have to explicitly supply a function that gives me the derivative of a value at a certain value. And not all functions are analytically defined. So not every function f has an analytic representation of the derivative. So we want to have a method to compute the derivative without having to know what the analytical representation of that derivative is. Well, what I just propose doing is to define a general function f prime, which takes the function itself, takes the value x at which I want to know the value of the slope, and it takes an epsilon, because we will need that for the computation. And if you think about it, the slope of a function, of an arbitrary function at some point here, can be computed dynamically by going a bit to the left, going a bit to the right, and just draw a line through these 2 points and take that as an approximation of the derivative of the value at point x. So in this case, I just divide epsilon by 50, which is completely arbitrary. You can play with that. It's just to measure how far away I want to go from my point. Compute the value of x, of f, at x plus delta and at x minus delta, and divide it by the distance, essentially. That's the delta y, that's delta x, and my slope is computed that way, right? So now we don't have to specify that f prime function anymore, because we have one function that always works. But the problem is, if we go from the code we had before, now we have to supply an f prime function which has a much more complicated prototype, if you want, right? Because the f prime now expects a function itself and takes 2 doubles, and we want to invoke it here with our 3 arguments instead of just supplying 1 argument. We now have to supply the function itself, we have to supply xn and epsilon, but otherwise the code is absolutely the same. So let's use turn that into a implementation or into use of our fixed point function. Well, remember, fixed point, it takes the max iteration and the init and 2 lambdas. The first lambda computes the next value of the iteration, which in this case uses f prime and does the computation in accordance to the Newton-Raphson method. So it divides the derivative over the function value at that point, and the termination condition is just looking whether the current function is close enough to 0 so that we can stop our iteration. Again, absolutely the same algorithm we developed once, but this time applied to a completely different topic, namely finding the root using Newton-Raphson. Okay, there are more methods, and I will not talk about those a lot. So there's a so-called Halley's method, which has a more complicated way of finding the next iteration. This one requires a contiguous second derivative, but it guarantees very fast convergence. There's Schroeder's method, which is very fast converging, and the benefit of that one is that it is known to work very well when you have several roots. So you will be able to find several roots, not one. So I wanted to give you those formulas because I think it's a nice exercise for you to implement those two methods, the Halley's method and the Schroeder's method, just by calling the fixed point function and do all the logic yourself. Please note that you now have to compute the second derivative, because both of them require the second derivative, right? Here's a second derivative, and in the Halley's method you have the second derivative as well. How do you do that? Well, you use your f prime function on the result of the whatever the f prime function has returned first. You find the second derivative essentially of your function. So all the tools you need for that are on the slides. So you just have to combine them in a different way, and you can compute Halley's method or use Schroeder's method to find the roots. Any questions about that? Okay. Last but not least, gradient descent. Gradient descent is not used for finding roots, but gradient descent is usually used to find minima or maxima of a function. It's used very widely in machine learning and AI. It's the main optimization method that is used today when it comes to training AI models. That's why I want to highlight that here, because this is one fundamental algorithm which is widely used in the industry everywhere. Okay, for that, let's extend the notion of a gradient to a function that has more than one independent variable, so a multivariate function, a function that depends on x and y or on a whole set of variables. And in this case, the gradient is defined as a vector of the partial derivatives of that original function at that point. So let's do an example. If you have a function of two independent variables defined like 0.5 x squared plus y squared, then the partial derivatives are over x is x and over y is 2y. So the overall gradient can be computed by putting the current value of the current point into that vector, and you get the gradient in that particular point of the function. So this function looks like this, just for you to visualize it, and it has a clear minimum which can be found using the gradient descent method easily. Okay, so gradient descent is an algorithm for finding that minimum or maximum for a convex and differentiable function. What I mean by convex? Well, first it has to be differentiable. That means it has to be contiguous. So the derivation of the function has to be defined everywhere. But that's kind of the precondition of all the methods I mentioned so far. So you can't do that for a function that has these discontinuities or some cusps in there. For those functions, it will not work. And it has to be convex. So the second derivative has to be, shouldn't change its sign. So this is a convex function. This is a non-convex function. You can certainly apply the gradient descent for the part of the function that is convex, but you have to be very careful not to exit the range of the convexivity of that function, because otherwise you might drop into infinity and you will not be able to find your minima anymore. Okay, so what does gradient descent do? It iteratively calculates the next point using the gradient at the current position Pn, where Pn is a vector of values I want in the multidimensional space that describe the current iteration point. You scale the gradient by some what's called a learning rate, and the term alone tells you that it's being used in machine learning very widely, and that learning rate is a parameter that is very crucial, and people always play with that to speed up the optimization, and we will see how that affects optimization. And then you compute the next iteration point by simply subtracting the current the scale gradient from the current position. So nu is a scaling learning rate which controls the step size. The smaller the learning rate, the slower the algorithm will converge, because the gradient will be scaled down. And if the learning rate is too large, it will jump around and it might not converge at all. So just to show you how that looks like, if we start at 0.0 with a very small learning rate, then you see that it's slowly going down until it hits the minimum. But if we use a very large learning rate, then it might jump around and it might not be even able to find your solution. So the learning rate is absolutely crucial, and it has to be selected very, very wisely. Otherwise, things will not work well. Okay, let's look at the algorithm. And you might already guess what's coming. Well, you can use our fixed point iteration, right? Because that formula just tells you we have one set of values, we apply some magic, and we get a new set of values, which is, again, a fixed point, a perfect use case for our fixed point algorithm. So what we need two lambdas. One lambda, which gives me the next point. In this case, it's a function of one variable, just for simplicity. I find the derivative at that point, and then I compute the next point by subtracting the derivative multiplied by a given learning rate from the current value. And my termination condition, obviously, is whether I'm close enough to my epsilon or not. So has the value of the function changed since my last iteration, or is it kind of constant? So again, our fixed point algorithm, which we haven't changed in any way. We have written it once and we have applied it for, I don't know, 5, 6, 7 different problems just like that. So that's the benefit of having generic functions which are well designed and which nicely encapsulate a particular functionality. By the way, I'm using the ampersand in the lambdas here, as you see. The ampersand stands for please capture all variables I need by reference. So otherwise I would have to list f prime, f, epsilon, and learning rate in the capture clause. But since I'm too lazy, I'm just saying, okay, capture everything you want and all you need by reference. By the way, if you want to capture things by value, you write it this way. Just the equal sign in the capture clause, which will capture all needed variables by value. So things get copied into the lambda, whereas these are not copied, but they are referenced in the lambda. So if they change outside of the lambda will work with the changed values afterwards. Okay. Another exercise. Implement the gradient descent for functions of 2 or more variables and use the fixed point algorithm for that. Should be straightforward. All the tools we have at our hands. And create a plot visualizing your results for varying learning rates. Use that function of 2 arguments I gave you. If you want to play with that, fine. The second exercise is a bit more difficult. Implement a second order algorithm that finds extrema for a given function. What do I mean by that? We have talked about finding extrema and we have talked about finding roots. And these two things are very closely connected because we know that at the point of the extrema, the first derivative has actually a root, right? The first derivative turns to 0 when my function of I'm deriving is actually has a minimum. So finding minima and finding roots are things that are very closely connected. And here comes essentially a rant. The whole community in AI is wasting gigawatts of energy. And we know that, right? We are running out of energy just because of the big companies needing more and more energy for ChatGPT and for all these things nobody actually needs. Why is it so energy and why can't they reduce the energy consumption of that? Well, there are several reasons. The first reason is these models have a very large number of independent parameters. Right? I showed you examples for one functions with one parameter, with one independent variable and with two independent variables. The AI and machine learning problems are optimization problems that optimize a function of millions or billions of independent parameters. So you have a function that is a vast distribution in a million-dimensional space, if you want. And in that function that is somehow defined in that space, it tries to find a minimum. It tries to minimize a loss function that allows us to derive the parameters we need for our machine learning model. So what the community is doing nowadays, they use gradient descent to find that minimum. And when they found the minimum, they have trained their model. Okay? The problem with these gradient descent methods is, and I haven't talked about that so far, is that they are inherently sequential. You can't parallelize them, right? You have to loop through it and you have to repeatedly compute the gradient until you get to the minimum. There is no way to parallelize those. And that's the reason why it's so expensive to train these models, because there's no way to parallelize all of that. And the whole community is trying to feverishly find all kind of tricks and all kind of methods to at least somehow parallelize these things. They come up with model parallelism and data parallelism and parameter spaces and God knows what in order to get a handle on distributing the computation across larger compute systems to speed up the overall computation. And the cause is that everybody is using first order methods, namely one derivative to find the minimum of those functions. Don't ask me why nobody is doing it, but what about if we, instead of using gradient descent on the actual function, we use the Newton-Raphson method on the first derivative? 2 iterations and I have my point, right? I found my minimum just by finding the root of the first derivative. And that is these methods are called second-order algorithms because they use the second derivative of the original function in order to find the root. Instead of finding the minimum, they find the root of the first derivative. And funny enough, these algorithms are perfectly parallelizable. So Newton-Raphson is an algorithm that can be perfectly parallelized. We might talk about that in a future lecture. There's a whole theory developed in the 70s and 80s of last century that describes how you can use these root finding mechanisms and how you can parallelize them, how you can distribute them across many machines. So instead of developing new algorithms, the whole community is wasting gigawatts of energy to do what they know how to do. So my message to you is, if you want to become a billionaire very quickly, apply the techniques we talked about today and develop second-order optimization algorithms and apply them to machine learning. And you will save energy by a factor of at least 1,000. So you will turn down the energy requirements from gigawatts to megawatts worldwide. Obviously, right? So invest some brain matter into that, and you will become the CEO of the next big company that will control the AI space. By the way, my suspicion is that the DeepSeek guys in China have done exactly that. Otherwise, they wouldn't have been able to do that. And if you become that CEO, just remember that I'm here and just say hello. And I'm happy to accept donations or something like that, okay? Well, that's it for today. Thank you so much for your attention and see you on Thursday.